All right, let's get started. Good afternoon, everybody. Welcome to a wonderful afternoon of Chem 170 Organic Chemistry with your host, me, Dr. White. And as you notice, I had a busy day yesterday. I graded all the tests. Normally, I give tests and the rest of the semester I should, other than the final, give tests on Wednesday, so I have plenty of time to grade them. And I always get them back the next class. Well, I figured I better get myself in gear yesterday, and I did. I had a 13-hour day. Everybody get their little violins out for me. But anyways, got it done. Now, listen carefully. I'm going to go through the whole test in a minute or two. I do that for every test. The final, I don't because it's the end of the semester. Uh, you should never, ever be penalized for a mistake I make in grading. That's why normally if we were face to face, I'd hand back your test and I'd go through it in class. If anybody had any problems, I say, write it down what I did wrong and let me know and I can look and I'll fix it if it's wrong. Because if I make a mistake, you shouldn't be penalized ever. Now, we don't do that here. You all should have gotten an email with the test score or points for each answer you put down. Now, one of the things that's different when I do it where I have a piece of paper versus I do that, I have it set up in a spreadsheet. I'll do a whole page in my head grading. Once in a while, I'll get two numbers transposed. And I did that to two of you, where problem 3 and 4A, where everybody got 3 right and 4, a lot of you got 4A wrong. I switched it. You got the same score, but I've notified two of the people who let me know. But always feel free to ask me about, first of all, there's no such thing as dumb question, and that pertains to why I graded something on the test. And I'm going to go through the test. Now, listen carefully. Do not ask me now, why did you take off points for this? Either come to my office hour tonight or after lab today, stick around, and I'll be more than happy to answer any of those questions for you. Unfortunately, I still got your tests on the other machine, but we'll work it out. And I will do that. And most of you did pretty good, and I'll talk about that after the test. All right, let's go through the test. All right, real quick. Everybody see test 1 on the screen? Thank you. By the way, this person, Key, always gets one of the top scores, always the best score. By the way, if you were face to face, I do something in the lab or I have students do a to-do list. I put my initials on here. I don't do that online. And if you notice, that's a K inside a W, KW. And it took my whole freshman year of non-Western civilization social studies class. I was bored out of my head. And I challenged myself to come up with a monogram. I got the highest score in that class, but the teacher was upset with me because he knew I wasn't paying attention, at least in his mind. But I was just working on another thing at the same time. But anyways, let's get to work. Also, if it's a 4-point question, make sure I gave you 4 points if it's correct. If it's a 3-point, and I may have given you 2, check on that. Those are common mistakes. Don't make many mistakes, but the last time I checked, I don't walk on water unless it's frozen. Even then, I stay off it. In other words, I can make mistakes. All right. Number 1, what's a hydrocarbon molecule? A molecule with only carbon and hydrogen atoms. Number 2, how many electrons are involved in a covalent triple bond? Each bond is 2 electrons. 3 times 2, 6. This one, well, this is my gift to you. How many bonds should a carbon have? 4. All right, this one a number of you had problems with. Let's go through it. How many carbons are in the longest chain of following? This carbon is connect to this carbon, connect to this carbon, connect this to this, to this, to this, to this, and this. If you count them, they're 9. A lot of you just counted across. If you look and go back to my problem set for this chapter, the alkanes, I have some like that. Like I said, they're practice problems because I can do stuff like that on a test. And I do. All right, next one, same question. What's the longest chain? This is straight across, 5 carbons. All right, now give the Iupac name for the following. This one, these are hard to give in all of organic chemistry. Partial credit, but I tried to. Remember, you have to find the longest chain, that's the octane. It's the alkane, and then there's a methyl group, and it's on carbon 4. So it'd be 4-methyl octane. Here, there are actually 4 answers I accepted. Notice you have a ring, 5 carbons, cyclopentane. On the ring, you have isopropyl group and propyl. And the correct Iupac way would be 1 isopropyl, 2 N-propyl, cyclopentane. Now, if you put the 2 isopropyl first and the N-propyl first and the 1 isopropyl second, I gave you full credit. If you had the numbers reversed, I gave you full credit. If you had the names and numbers reversed, I gave you full credit. Remember, one of the card, you try and number in a ring or even in a ring, so you give both of the alkyl groups the lowest numbers. Therefore, one of these have to be 1, the other 2. All right. I think everybody but one person got this wrong. And this is a tricky one, but there's 5 bonus points, so I feel I can put a couple of tricky ones down there. Let me explain. What's the longest chain? 1, 2, 3, 4, 5, 6, 7, 8, 9. If you got the base name wrong on any nomenclature problem, I give you 0 points. So the longest chain is 9, no name. With that, and I've outlined that longest chain with this black line, and that leaves a methyl group here, and a T-butyl or tert-butyl group here. This is 1 methyl group is on 3, T-butyl on 4, the other methyl group is on 5. So that would be 4 tert-butyl or T-butyl, 3,5-dimethyl, no name. Now, if you had put the 3,5-dimethyl first and the 4-T-butyl second, I'd still give you full credit. And that's how you do this one. And this is a hard one. And I do something similar in the past, and students, most of them are, how should I say, just look at the one straight across. Number 6, 3 points each. Draw the condensed structures for the following molecules. Be sure to put in all necessary hydrogen atoms. Let's use line structures for rings and other too. I think one of you did both. You don't have to, but anyways, start from the right, move left. Cyclopentane and butyl, 4 carbons to the N carbon. You could have put this on any one of those carbons in the ring. Next one, 4 tert-butyl, 2-methyl decane. Start from the right, decane, 10 carbons. Next, methyl group on carbon 2, and my favorite, the T-butyl group or tert-butyl on carbon 4. Now, this is a common name, and on my test, I'll never ask you what's the common name for a structure, but I will ask you to be able to draw the common name. And in this case, acetylene is the simplest molecule with a triple bond, 2 carbons. And you can write it this way, and this is called left justified hydrogen here, or right justified. Either one is correct. D, 7-methyl 5-isopropyl cis-2-nonene, ENE ending as we're going right to left. If that were ANE, 9 carbons, ZNE, double bond, starts at carbon 2 and it's cis. That means hydrogens are on the same side. 1, double bond starts at 2 to 3. The hydrogens are on the same side. And then we have the rest of the 9 carbons. On carbon 5, we have an isopropyl. And on carbon 7, we have a methyl. One thing I should warn you, I've got one of the fastest mouse wheel fingers around. And if you're writing this down, tell me, don't move or something like that. Everybody ready for me to move forward? Okay. All right, next one. And now you know I asked things like, well, I asked a million times, did you think about gasoline when you went by a gas station? Or did you think about alkanes? And the question is, name a commercial available item with an alkane in it that you could use in your daily life. Propane, like for your barbecue, gasoline, candles. You could have put down Vaseline baby oil, and those would all be good examples. All right, number 8. Give the Iupac name for the following organic compounds. Ooh, triple bond. How many carbons in the longest chain? 5. Pentane, triple bond, pentyne. And what's the lead carbon of the triple bond closest to the end? It's on carbon 2, so it's 2-pentyne. And next, ooh, a double bond. How many carbons longest chain? 1, 2, 3, 4, 5, 6, 7, 8. Same thing here would be 6, 7, 8. And therefore, I'll take that. Octane, double bond, octene. The carbon closest to the other double bond to the end of the chain is 2, 2-octene. The hydrogens are on opposite side here and here of the 2 lines or the plane coming out from the double bond, so that's trans. And then this is carbon 2, 3, 4, 5, 6. We have an ethyl group. And finally, I taught you this has the structure, the name benzene. Now, one thing I should point out, one of your colleagues did, and I'll explain why I grade the way I do. If you give me 2 answers and say this or this, and one of them is wrong, I mark the problem wrong. It's not my job to determine which is the right answer, which is the wrong answer. It's your job. So remember, if you put down more than one answer for a namesake, because you're not sure, pick one and go with it. Because if one is right and one is wrong, I'll mark the whole problem wrong. It's not my job to figure out which one is right. It's your job. All right. Number 9. How many pi bonds are in the following molecule? Double bond, 1 pi bond. I've said it about a million times, maybe not many, but lots. Triple bond, which I also said a lot, 2 pi bonds. Added up, 3 pi bonds, and that's how you got that number. All right, number 10, 3 points each. Give the organic reaction products for the following reactions. And what do we have different? Double bond, hydrogen and platinum. Hydrogen and catalyst break the pi bond. Each carbon gets a hydrogen, and you show that in a ring by getting rid of that line. Remember, you don't break carbon-carbon single bonds. That's why the methyl is still there. Next one, ooh, triple bond, excess bromate. Triple bond, halogen, where X is fluorine, chlorine, bromine, or iodine. You break the 2 pi bonds, each carbon gets 2 halogens. Do you break carbon-carbon single bonds? No. So I have 1, 2, 3, 4 carbons. I end up with 4. The 2 carbons with the triple bond are now the 2 carbons. Each one has 2 bromines. Next one, ooh, double bond, HBr, HX, where X in this case can be chlorine, bromine, or iodine. You break the pi bond, 1 carbon gets H, the other gets X, follows Markov-Nikod's rule. The carbon with the most hydrogens gets the H, and the other, in this case, will get the Br. This carbon has 0, this has 1, and therefore the hydrogen goes here, the the bromine goes there. You have 4 across and 1 methyl, 4 across and 1 methyl, and bromine there, hydrogen there. You got these switched. I didn't give any partial credit because the important part of this problem was, do you know how to apply Markovnikov's rule? All right, next one. Ooh, this molecule with excess hydrogen and a catalyst, platinum. But I see a double bond here. No, there are 2 double bonds, but they're separated by more than 1 carbon, so each one is independent. And because I have the letters XS, that means I have all the hydrogen in the world that hydrogen will react with and will. And what does it do? Any double bond, hydrogen and catalyst, catalyst can be nickel, platinum, or palladium. You break the pi bond and each atom gets a hydrogen, carbon atom. You break carbon-carbon single bonds? No. 2, 4, 6 across, 2, 4, 6 across. Break this pi bond, each carbon gets a hydrogen. Break this pi bond, each one gets a hydrogen. Next one, double bond. Reacting with acid and water. Double bond, acid and water, you break the pi bond. Think of water as HOH. 1 carbon gets H, the other gets OH. It follows Markovnikov's rule. The carbon with the most hydrogens gets the hydrogen. Remember, the rich get richer, poor get poorer. And the other carbon gets the hydroxyl. In this case, this carbon has 2 hydrogens. This has 0. The hydrogens go there, or hydrogen, and the hydroxyl group goes there. You have 1, 2, 3, 4, 5 across with a methyl. 1, 2, 3, 4, 5 across methyl. Hydroxyl group here, hydrogen there. Ooh, double bond. And iodine has double bond with a halogen, or X is either fluorine, chlorine, bromine, or in this case is iodine. You break the pi bond, each carbon of the double bond gets a halogen. In this case, the iodine. 1, 2, 3, 4, 5, 4 across. 5th one's right here. You break the pi bond, and each carbon gets an iodine, the halogen. Ooh, triple bond, excess hydrogen, a catalyst. Triple bond, 2 pi bonds. When I break those, each carbon of the triple bond gets 2 hydrogens. And therefore, 1, 2, 3, 4, 5, 1, 2, 3, 4, 5, because you don't break carbon-carbon single bonds. And each carbon of the triple bond got 2 hydrogens. Well, ooh, this is interesting. A double bond here and another one way at the other end, separated by more than 1 carbon, reacting with HBr, but excess. Remember, excess, because organic chemists don't like the balance equations unless we have to, tells you I have all the HBr, or hydrohalogen gas, to react with anything HX will react with. X is a halogen, double bond HX, that's not a plus, it should be an X. And you have X being chlorine, bromine, or iodine. Break the pi bond, 1 carbon gets H, the other X. What does that follow? Markovnikov's rule. Carbon with the most hydrogen gets the hydrogen, the other halogen. So this, we have 6 carbons across, 6 across. This double bond, H goes there, 2 hydrogens, halogen there, 1. There we go. This one down here, H goes to this carbon, halogen goes to this one, and there we go there. And finally, not finally, but next, we have a double bond in a ring. Dr. White, Mother Nature loves this. Rings and double bonds and rings. Students don't. Why? Because double bond acid and water, think of water as HOH, break the pi bond, 1 carbon gets H, the other gets OH, follows Markovnikov's rule. The carbon of the double bond that has the most hydrogen gets the hydrogen, the other gets the hydroxyl group. Oh, you don't see them there, but remember there's 4 bonds to carbon. 4 minus 3 means there's 1 hydrogen there. 1, 2, 3, 4. 4 minus 4, 0 hydrogens. which is greater there. Hydrogen goes there. You don't show it in the ring. Hydroxyl group goes there. And if you had these two switched, that would be all right too. All right, next one. Give all, this is unusual for Dr. White, but I have it, all the reaction product or products for the following reaction. If we look at this and say, what's different? Carbons, hydrogens, carbon-carbon single bonds, that's all. It's an alkane. I'm reacting with oxygen. It could have been a cycloalkane, alkane or cycloalkane, oxygen with a spark, which I don't show, and that's combustion. You make CO2 and water, so the answer is carbon dioxide and water. All right, continuing on. First of all, I'm going to take a water break. Continuing on, give the Iupac name for the following aromatic compound. Bromine, Br, is bromo on a benzene ring, bromobenzene. Now this one I took off one point if you didn't use ortho-para, but you use numbers instead, because this is what I want you to use, because most organic chemists like Dr. White do use that. And here we have benzene ring with a ethyl and N-butyl, and therefore this is para 1,4, and I took two different answers, para N-butyl ethyl benzene or para ethyl N-butyl benzene. Next one is one I did in class. Remember, the methyl group on a benzene ring is toluene. When it's more than one substituent in our class for this chapter, methyl group is 1, NO2 is nitro 2, and on carbon 4 and 6, so that'd be 2, 4, 6, trinitrotoluene. And, oops, that's not what I want. Whoever drew the nice little picture for me, thank you on their test. Someone did a stick of dynamite and boom. All right, next one, next page. Give the organic reaction products for the following. Ooh, what's different? Look for what's not carbon, look for what's not hydrogen, what's not a carbon-carbon single bond. Carbon, carbon, carbon on this carbon with the big dot in the center. Let's do a smaller dot. That's better. For this one, what do we have that's different? Carbon with a halogen, alkyl halide, where X can be chlorine or bromine. Ooh, a benzene ring, and aluminum trichloride. And this is Friedel-Crafts alkylation. You replace the hydrogen with the R group from the alkyl halide. The carbon with the halogen is the carbon bond to benzene. If you did that wrong, I either took off a point or maybe gave you 0. I forgot how I did it. In the future, it'll be 0. It's not to the right carbon, but it's the wrong product. And here's the product you get. Next one, bromine ferric tribromide. The general reaction is halogen plus FeBr3, and X can be in real life mainly chlorine or bromine. And what happens is you replace one of the hydrogens with a halogen. In this case, it's bromine. And this one, oh, you didn't write the general reaction? Well, this is. Take a benzene ring, nitric and sulfuric acid, and you get nitro group on a benzene ring. If you put HNO3, I think I gave you 0 points because that doesn't exist. Next one, no general reaction, because this is the general reaction, because I didn't have directors on the test, but we'll do that in the lab today. And that is benzene ring, sulfur trioxide, sulfuric acid. You put a sulfonic acid group. Remember, this needs a hydrogen there too. You just put SO3. I marked it wrong. All right, and the last one, most of you got wrong. Let's go through how you do this one. What's different in the product? Because you're asked, what is the structure of the starting material that you would need to make the following product via the reaction below? What do you react with HI to make this? Well, the first thing you should notice is what's different. And iodine on a carbon. And notice next to it, you have a carbon with a hydrogen, and you're reacting something with HI. How do you get to that? You have a double bond. Now, watch closely. The carbon here with the iodine, in this case with the halogen, has to be one of the carbons of the double bond. And I drew the structure so there'd only be one answer. And if this has to be in a double bond, an adjacent carbon has a hydrogen in the product, then the double bond is to this carbon. And therefore, this is the answer, because the rest of this over here, is this R coming along for the ride. And some of you gave me this answer up here. And remember, I keep on telling you, check your answers. This has 5 bonds to carbon. That's not going to happen. The other possibility, which would also be wrong, which is why I drew the structure, that he tried something like this. I can't even draw it wrong. This is wrong. Why? Look at this carbon. 1, 2, 3, 4, 5. No. Remember, which is why I put it on the test question, 4 bonds to carbon. And that's why there was only one answer. That's why I put the methyl group there to block that carbon. Otherwise, there would have been 2 possibilities. And that's test number 1. Now, if I made a grading error, send me an email, look at which ones you want me to regrade, or you can come to my office hour tonight, or stay after lab if you have any questions. Now, one of the things, if I were in your position right now, a question I would ask is, what grade am I getting in this class right now? Well, first of all, since I dropped the lowest test, each and every one of you has the opportunity still to get an A. Some of you might have a little more challenging road, but you can. I've had students not do good on the first test, then figure out, well, I better do the practice problems and study more. And they do well. If you need any help how to do better on tests, always feel free to ask me. Tom, do you have a question?
Yeah, I just want to know what the high grade was.
Okay.
If I could ask.
Yeah. Oh, you can. I won't tell you who it is, but I can say, I believe the high grade was 102. Remember, there was 5 bonus points. So theoretically, you could have gotten 105. And the person got that one wrong where I have it's no name. Most of you put down octane. Nope, wrong. But I sometimes a little tricky on only 1 or 2 problems. But that's why I do 5 bonus points so I can do that and not feel guilty. But that's how that was. I can't remember the average. Monday I'll try and remember, but I'm going to guess it was in the upper 80s, low 90s, somewhere in that range. I might.
Yeah, I was really stumped on that last problem.
Well, that's a hard one. I'm, but did you see the philosophy, how I showed how going backwards?
Yeah, now, yeah, I
Well,
was just stumped.
yeah, well, guess what? You weren't the only one. So, and every semester I give a problem like that in the first test, excuse me, and students have difficulties with it. But that's how you learn how to do more challenging things. All right, now, question you might have right now, like I said, what grade am I getting? Well, if you want a quick approximation, even though everybody can still get an A, because some of you, this might be your drop test, is if you look at my syllabus, and we've only got one test, and we got tons of points more. If you got a 90 and above, you got an A on the test. If you got 80, 89, B, 70, 79, C, and I don't think anybody got below that. It makes me happy because I like to see students do well. If you're having problems with the test, always feel free to come and see me for help, and I will. And I've helped students who need a little extra help or guidance, and that's test number one. Any questions about test number one? Any questions or anything like that? All right. Like I said, every test we take in this class, I will go through just like I did today. All right. Everybody see ethers and epoxides on your screen now? Thank you. All right, just a quick reminder. We're talking on Monday about ethers. Ethers are a molecule that have an oxygen and two carbon or R groups bonded to it. Example would be and I showed you the common name, name each R group as an alkyl group and add the word ether. So this would be ethyl, methyl, ether. Since this is a common name, hold on one second. All right. Once in a while, I got too many things going on open on the computer, so I'm doing a lot of computing here. I think I forgot to shut down something, which I should have. Let's see. Yep. It locks up momentarily. So this would be ethyl methyl ether. Since it's a common name and I didn't spell it right. You could also call it methyl ethyl ether. And I showed you the Iupac briefly. We will never have that on a test. Iupac, just the common names. Now, I talked a little about how ethers are very flammable. And we started on the Williamson ether synthesis. You react an alkoxide, and that's what this is called. And yes, there's nomenclature for these things, but I won't get into in this class. And alkyl halide, and there's nomenclature there, but I'm not going to get into it. And you make an ether plus salt, NaX, where X here, I don't have it here, is chlorine, bromine, or iodine, not fluorine. And remember the carbon with the halogen. The carbon with the halogen is the carbon oxygen is bonded to an R prime. And if I did the following reaction, I'll do this one, then I'll get you some to share too. If we look at this, we say, ooh, what's different here? Oxygen with a negative charge and a sodium cation with carbons. This is an alkoxide. Carbon with a halogen, Rx, where X is chlorine, bromine, or iodine. And what do you get? This attacks that. Organic chemists are violent. Instead of saying bonded to it, we actually do say it attacks it and bonds to it. Now, I'm going to show you this and I'll explain why later. But if I'm asking for the organic products, you don't have to put down the salt NaX. So what's R? Methyl. What's R prime? Isopropyl. This oxygen will bond to the carbon with the halogen. So I have methyl, oxygen, 3 carbons there, and R prime, I better end up, and it's to the center of 3. And I've just made methyl isopropyl ether. Now, it's your turn. And what would be the product or products for the following reaction? Psst, you're doing organic chemistry, very sophisticated stuff. Aren't you proud of yourself? You should be. And when you're done, give me a thumbs up. And if you finish early, I try and give everybody time to finish, so please be patient. All right, I think, is everybody done? Okay, let's do it. Now, and I'm going to say this all semester, but it's true for me and organic chemists. We look at a molecule and look for what's different. Why? Because that's where all the fun and action is, always. And what's not a carbon-carbon single bond or carbon or hydrogen should get your attention. Ooh, look, oxygen with negative charge with a carbons on it and a sodium cation, alkoxide. Carbon with a halogen, carbon single, alkyl halide. Remember, X can be chlorine, in this case, bromine or iodine. And this attacks and bonds to the carbon with the halogen, it's lost. Now, for the problem, you don't have to put down any X, but I'll explain why I do that later. So what's R? 2 carbons. What's our prime? 1, 2, 3, 4, 5 carbons. Now notice this second carbon has the bromine attached to it. Do you break carbon-carbon single bonds? And the answer is no. 1, 2, 3, 4, 5. Which carbon had the halogen? This one. That's the one bonded to the oxygen. And what's on oxygen? My R, 2 carbons. This is one way of drawing it. There are other ways you could have drawn it. And that's how you do it. Oh, let's do one more. First of all, anybody need more time seeing this? I guess you're all good to go, so I'm going to go. Let's do one more. Here's one for you. What would be the product or products for the following reaction? And I could just as easily have drawn it this way. And this is cyclohexane, not a benzene ring. Before I forget, and I almost did, on Monday, I will be going through the alcohols problem set. So I highly recommend you try it before we go through it on Monday. And yesterday, for those of you who cook, even though I was busy, I made time because I had some milk I had to use. And I first made a roux, for those of you who know what a roux is. And then I made a bechamel sauce, which you can freeze that stuff. And so my freezer has a nice amount of bechamel sauce whenever I need it for something. And that's Dr. White's cooking announcement for today. And when you're done, give me a thumbs up. I think everybody's done. Let's do this. All right. What do we have that's different? Ooh, oxygen with a negative charge, sodium cation. And therefore, ooh, carbons. This is, let me give myself a little more room, an alkoxide. Ooh, if we look at this ring, what's different? Carbons with a halogen on it, that's an alkyl halide. Remember, X can be chlorine, bromine, or iodine. And this attacks that, kicks out the halogen, you make a salt, and you also make the most important thing, an ether. Now, what's our methyl? What's our prime? Cyclohexane. Now, you could draw it this way. Or there are other ways you could have drawn it. I could just as easily have drawn it this way. Cyclohexane ring, R group, and then methyl. Both cases, that's methyl cyclohexyl ether. I'll never ask you the name of that. This can be a substituent called cyclohexyl ring. And that's how you do it. Let's look at the clock. Let's take a 5-minute break now instead of me rushing through the next problem. We're starting a little early. I'll still get you out at a decent time today before midnight. But anyways, come back 5 minutes, 1:50, and we'll continue on. And we'll do our lab today too. All right, let's get back to work. Ring, ring. Oh, wait. That get everybody back? All right, let's get back to work. Now, I was talking about the Williamson ether synthesis, and unlike test one, where we only had, hold on one sec. That's better. We only had one synthesis problem. On test 2, 3, I'll probably have about 3 or 4. I won't do all of them because that would be cruel and unusual punishment. And up to now, the Supreme Court has outlawed doing that to students. May change in the future, but so far it hasn't. I hope it never does. Now, the other thing I should mention is for test 1, especially the first week or two, I spent a lot of time on nomenclature. For test 2 and test 3, I'll spend more time on reactions and less on nomenclature. I'll still cover nomenclature, but I don't have to teach you how to find the longest chain and things like that, because you've learned that lesson, I hope. I think from the test scores you have, except the one I tricked you on. Yeah, Dr. White. But anyways, with that in mind, I'll tell you more about it right before test number 2, but just to give you a heads up, test number 2 will have about 60, 65 points on reactions, about 30 points or so on nomenclature, a lot more points on reactions, and about 5 or 10 points on general knowledge. Ooh, speaking about general knowledge, did anybody happen to drive by a gas station and think about alcohols? Because if you look at the label of a gas pump in the northern Illinois area, it says this gasoline contains up to 10% ethanol. Next time you're in a gas station with a friend, you can point to that and say, you know, that's an Iupac name for an alcohol. No, don't do that. But, or did you happen to pick up a bottle of rubbing alcohol and see it's got isopropyl alcohol, which is an alcohol? Or, and if you're not underage, if you're underage, don't do this, but do you happen to be in a supermarket or a liquor store and see the good stuff and you like vodka or Canadian Club or amaretto? I like that. And think about that's got ethanol. Only if you buy it if you're proper age. Remember, organic chemistry is all around us. When you leave my classroom or our Zoom meeting, you can still think about it. All right, let's look at a synthesis problem. And let's look at the following. And I will be nice when there are 2 starting materials or more than one product, I'll show question mark. All right, why am I getting a memory error? I'm going to close something out for now. All right, I've never gotten before. All right. And the question would be, what do you start with? What 2 things do you start with and react to make these products? And now we look for what's different. Ooh, an oxygen, carbon's here and here. This is an ether. Ooh, and we're also making salt, NaX. And here, what's X? It's a halogen, chlorine, which in this case it is bromine, or iodine. And now, if we come back here, how do we make an ether? Alkoxide plus an alkyl halide. So I'm going to call this R, and this R prime. And therefore, what would be my question marks? I'm going to move down here. You'll understand why in a second. Well, R is methyl, so this would be that product. If I look here, R prime is ethyl. If I move my picture here, and you see what's X, chlorine. So this would make the products I want. But wait, what if I say this is R prime and this is R? And I can. And therefore, my alkoxide, R, would be ethyl. Remember, the carbon bond to the oxygen here is the carbon with the alkoxide here. And what's my R prime here in red? Methyl. And what's my halogen? Still chlorine. And lo and behold, if I react this, I'd get the same product. And this happens in a lot of organic chemistry where there's more than one way you can make something. And the question is, which one is correct? And the answer is they both are. Now, on a test, they both are correct. Now, in real life, how does someone at my level, not yours, in fact, at ECC, there's only one other chemist who probably could do what I'm going to tell you. The rest of them don't have the experience higher than that other chemists have, which is the better reaction. And the way you do that is called cost accounting. Which one has the lower direct cost, which means expense to buy those chemicals. And because I've worked with that for many years, I know that the one in red is going to be cheaper than the one in black, because I know the prices of these chemicals. And methyl chloride is cheaper than this, and these are about the same price. So that's why I would say I would go with red if I were in industry, because that maximizes my profit. But on a test, either one of these is correct, because I don't expect you to know cost accounting.
I have a question.
Yep.
You know, I missed Monday.
Right.
When you go back to your little whiteboard.
Yep.
I just don't know what the R, with the smiley face sticking out of his head is.
All right. Let me, when you have carbons, R means anything with carbons and hydrogens. Okay, it's like X and Y. And then we have an oxygen.
Okay.
Oxygen has a negative charge. All
Okay.
molecules must have a net zero charge. So I need a cation and most sodium. Now, what I teach, we'll learn in a lab later on semester, but I won't have it on a class. If you take an alcohol and react it with sodium, you'll make that.
Okay.
But this
so oxygen negative charge, that's what that means. Okay. Thank you.
It does look like a smiley face.
We're all happy.
Well, a negative charge on oxygen is happy. Everybody's happy like that. But anyways, that's how you do it. And I was about to, now I got my train of thought back. After I got into industry, I found one of the things I should have done in undergrad or grad school was, guess what? Take a course in accounting. Because when I got into upper management, I went into a meeting and everybody's talking about gross margin, EBITDA, and things like that. I had no idea what they were talking about. And one of my colleagues said, go get an accounting book and learn it quick. And I did. And I have learned it. And it's an important thing in chemistry because when you work for a company, you're always trying to make maximum profits. An important aspect of that is accounting and cost accounting, determining if you're going to make something, how much will it cost? Because if you're making products for a certain industry, you know how much that people will pay maximum for something. Example, you don't think of it, but nail polish is very high level organic chemistry. How many people do you know would pay $1,000 for a small bottle of nail polish? Probably none. So you have to keep your raw materials, what you react in a way that the cost plus your profit is something that people will still buy. And that's why I wish I had learned accounting before I had to teach it myself in a crash course. What I did was I called up my accountant at the time. This was before TurboTax. I use TurboTax now. But I got to do that next couple of weeks. But anyways, and I asked him, do you have a good book on accounting that I can learn the basics? And he said, come on by, because he was a friend of my brother-in-law's. I'll lend you one of my accounting 101 books. And I sat down at night and started learning it. But anyways, time for you to have some fun. And the question would be, what two things do you have to react to make this compound? And this reaction, you also make this compound. Your turn. And when you're done, give me a thumbs up. I see one person done. 2, take your time. I try and give everybody time to do this. It's new stuff, and sometimes maybe a little challenging for you. All right, I think everybody's done. Let's do it. Now, how do you do this? First of all, look at what you're trying to make and say what's different. What's not carbon, what's not hydrogen. Ooh, an oxygen with carbons here and carbons here. This is an ether. Ooh, a salt, NaX. Remember, X equals chlorine, bromine, or iodine. How do you make ethers? Well, the best way, and the only way, there's another way, but this is much better, and that's the Williamson ether synthesis. An alkoxide plus an alkyl halide. And I can say this is R, and this right here, isopropyl R prime. if that's the case, R is ethyl. And I have an alkoxide. And then my R prime, the halogen is on the same carbon that the oxygen is bonded to in the ether, which is the center one. So I have an isopropyl group. Just think 5 months ago, you would know what an isopropyl group is. What's my halogen? Bromine. And that's the way to do that. But wait, I could have also said, this is R prime, and this is R. The oxygen here is on the carbon in R that the oxygen here is bonded to. So I have my isopropyl group here. Then my R prime is 2 carbons, and one of them has the halogen bromine. And the question is, which is the right answer? For this class, either one is correct. And that's ethers. Well, I have this on the board. This will never be on a test, but ethers are excellent solvents because they're very unreactive, other than you can burn them. But other than that, they're very unreactive in most instances. And as I mentioned the other day, a very widespread ether is diethyl ether. But I did my reactions for my PhD thesis. And let me introduce you to an old friend of mine. This is called the cyclic ether. This has got a common name of tetrahydrofuran, also known as THF. I use gallons of this stuff, lots of it. I had to purify it too. But anyways, that's an oxygen in a 5-member ring, 4 carbons and 1 oxygen. And it's an ether. Oxygen, R prime. Just so happens they're connected together in the ring. But this will never be on a test right here. But I thought I'd remember an old friend of mine. Now, you know I'm an organic chemist. All right, let's continue on. Okay. Hold on 1 second. All right. I don't know why sometimes this computer does that. All right, sorry about that. Somehow it locked up in Word, and I know how to go to close it and come back. But anyways, guess what time it is? It's new functional group time. Boy, we're moving along. It's a new functional group. And this new functional group I've worked with in the industry, and it's called epoxides. Now, one thing I should warn you about, I will be getting into, now that we're getting into the juicy stuff, really good stuff, I'll be getting some things that these chemicals are used for. And in no way am I taking a moralistic view of the use of these chemicals, whether it's right or wrong. It's just that they're used for that and they're in our daily life. So I'm going to talk about it. And what's the new functional group? It's an epoxide. Now, an epoxide, at first glance, you think, oh, this is an ether right here. Carbon, carbon, they're connected together, but each one. But no, this has different chemistry than ethers. And because of that, they, meaning chemists, had to give it a name as a functional group because it does not react like an ether. It reacts totally different. Now, for this class, I'm not going to go through nomenclature of epoxides. In fact, I'm only going to talk about one epoxide. That's when the 2R groups here, 2R groups here are actually hydrogens. And this has the common name. I don't even know the Iupac name because I don't know anybody who uses it. It does have, there are, but this is called ethylene oxide. On a test, I'll never ask you the structure or the name of ethylene oxide. Ethylene oxide, I'm going to try to be good. What do I mean by that? If you work in the industry with ethylene oxide, you actually call it EO, but I'm going to stay away from that. Now, ethylene oxide is quite hazardous material. If you get enough oxygen in it under the wrong conditions, it explodes quite violently. And one company I worked for where we used ethylene oxide, we had the chemical plant and about a couple hundred yards away, the research center. And then they had two, 500,000 pound storage tanks of ethylene oxide. Now, this company then was called PPG Mazer, and it's been bought out by someone else, and was about 4 miles northeast of Great America. One afternoon when it was Friday and we're finishing up, a bunch of us are sitting around the lab, someone asked, if our ethylene oxide tanks blow up, will we take out Great America? And we talked about it, and the consensus one, first of all, we'd be dead instantly. The Neo tank, I said I wouldn't do that, bad Dr. White. The ethylene oxide tank, 500,000 pounds blows up. You've got about at least a 300-400 yard crater where everybody in that area was dead, which would have been us. But we figured the shock wave from that explosion would shake up Great America, but probably wouldn't kill anybody. Nice thoughts. Ethylene oxide is very dangerous. I remember the first time I used it in industry, I didn't use it in the grad school. My hands were at first like this. I said, calm down. And someone showed me the safe way to use it. And you take your time and you use it, do it safely. And when you go into plant, the first time you supervise, we're using 10, 12,000 pounds of ethylene oxide. Are you doing everything right? Oh, I was in high alert. Then you relax and still are in high alert. And so are the workers always. All right, now ethylene oxide is an amazing chemical. The next page, I'm going to turn the switch off. You never want to have water when you're working with ethylene oxide. Now, it turns out these bonds between the oxygen and carbon to form this overall three-membered ring are very strained. That means they don't want to be there. If I can find a way to break, I will. And water will break that. Hold on 1 second. Two more rings. One more ring. Ah, they gave up. Good news, it wasn't the president or Senator McConnell either. I don't know them, they don't know me. But anyways, let's get back to ethylene oxide. And what happens is you break one of these bonds with water, will do it quite easily, and the H goes to the oxygen, and the OH goes to this carbon. And you've just made the most expensive way of making ethylene oxide. ethylene glycol from ethylene oxide. In other words, when you do a reaction with water with ethylene oxide, you make sure there's no water around or you waste all your ethylene oxide. But now I'll turn the switch on. If you take an alcohol, and I can also write it this way, and react it with ethylene oxide, same thing happens. You're going to break one of these bonds. The H goes to the oxygen, and this OR goes to the carbon. And notice this molecule now has two functional groups. Right here, you have an ether. And right here, you have an alcohol. And this is an ether alcohol. And turns out this type of molecule are used in many things, some personal care items, and I'll talk about a couple in a little while. So switch is full on. Let's go through some examples. Now, this kind of reaction happens with other epoxides, but I'll only talk about in this class ethylene oxide. So what would be the product or products for the following reaction? What's different here? Carbon, hydroxyl group, alcohol. What do I have here? Ethylene oxide. What do you get? You get a poly or a ether alcohol. Now, what's our ethyl? So I'll write my ethyl group, my R group. Now I'll write the rest of this. O, CH2, CH2, OH. And I've made that ether alcohol. Oh, that was fun. And I've done reactions with different alcohols, both in the lab and in a chemical plant. Ooh, do I have time? I do. Quick Dr. White story. At that company I told you in Gurnee, one of the reasons I was hired is they were having troubles with the quality of their products they're making there. I was asked to come in and improve that and also improve their quality control lab because I'm one of the few PhD chemists who's ever managed one of that. I wasn't made manager. I was just asked to come in. I knew that job would only be for a year or two. Well, anyways, one of the tests I had to improve on to do some measurements, someone at the research lab in Pittsburgh, the company at that point that owned that plant was PPG, Pittsburgh Plate and Glass, and it was called the Maser division of PPG. And I go into my boss, I said, who wrote this test that we use when we're measuring, is the reaction done? Because it needs to be improved. I would like to talk to him. And he said, Dr. Dahmer. And one of the things I've done throughout my life, and I don't know how I do this, I say something in jest that's actually true. And people, how do you know that? And so I said, that's not Jeffrey's father, is it? I don't know if you're familiar, Jeffrey Dahmer, a horrific person who killed a bunch of people in Milwaukee and ate them. Well, anyways, my boss said, yes, and don't bring up his son with him, please, ever. And every time I talked to Dr. Dahmer, who was a nice guy, I never met him face to face. I saw him on TV once or twice after I left the company when he was interviewed, but it was when his son was killed in prison. But I always wanted to ask him, what happened with your son? And it was always weird. In the back of my brain, it's saying, ask him. And the other part says, no, you don't. I never did, thank goodness. But that's a strange life story. Yes, I did work with Dr. Jeffrey Dahmer's father. But anyways, back to here. I better give you a chance to do one. Your turn. What would be the product or products for the following reaction? Well, every time I bring back that memory, I go, oh, wow. Life can be stranger than fiction many times, and I'm a witness to that personally. And when you're done, give me a thumbs up. If we were in a classroom, I'd say, when you're done, look up and smile. I'd see all those smiling faces. Or I said, if you want, you can also frown. All right, I think everybody's done. Let's do it. What do we have here that's different? That's what I always look at a molecule. What's not carbon? What's not hydrogen? Ooh, hydroxyl group on a carbon? That's an alcohol. Ooh, a three-membered ring with an oxygen? This is ethylene oxide. And what do you get? An ether alcohol. What's our isopropyl? So therefore, I'll have my R group. Note the carbon with the hydroxyl group is the carbon that this oxygen will be bonded to. Oxygen, CH2, CH2, OH. And that's what you get. Now, it's time for a little gift from Dr. White. Remember, a little gift. On my test and my final, I will never give anything with ethylene oxide as a synthesis problem. Students tend to have trouble with that, and therefore I won't do that. Again, this reaction, another one which I won't get to today, any reaction with ethylene oxide, it's my gift to you. I won't put in a synthesis. The regular problems, yes. Synthesis, no. Let's do one more. They're fun. And why don't you try this one? What would be the product or products for the following reaction? I see one person done already. Oh, another one. See, organic chemistry is fun. Anybody need more time? Going once, twice. All right, let's do it. If I look here and I say, what's different? Ooh, oxygen with a hydrogen and a carbon, alcohol. What am I reacting with? Ethylene oxide. See, I've been good. I haven't used slang we use in the chemical industry. And what do you get? An ether, alcohol. And if we look at this, what's our N-butyl? Do you break carbon-carbon single bonds? No. So I'm going to have 4 carbons. That's my R group. Which carbon has the hydroxyl group will be the carbon this oxygen is bonded to, the end one. And then I'll get the rest of it, CH2, CH2OH. And here we have that molecule. All right. One of the things you should be asking yourself more and more in my class now, because we're getting into the juicy stuff, good stuff, why am I learning this? And the obvious answer is you want to get a good grade because you want to get into a class or a school or a program, and you need my class for that. But the real, why are you learning this? Let's take a look at this molecule you just made. Wrong one. Right one. This is called 2-butoxy ethanol, which you don't have to know because I'll never ask you to name it. But this is a molecule. One place this is used then, it's the key ingredient in the easy off cold oven product. If you have an oven and you want to get it clean, you don't have one of those, you crank up temperature and it burns off stuff on the surface. Easy Off has made products for many years. One of them is you got to heat the oven and then you spray some stuff in there. Stay away from that because it's quite hazardous. I think they use lye or sodium hydroxide. Don't quote me on that. The other one is you have a cold oven, you spray it, let it sit for a half hour and wipe it right off. And it works quite good. I do my sister's oven every once in a while for her because she doesn't want to handle her. My brother-in-law unfortunately passed away recently, but even when he was around, they didn't want to handle chemicals. You're a chemist, organic, you do it for us, and I do. Anyways, it works good. Now, molecules can be used for things that are beneficial and sometimes not beneficial. How many of you are familiar with Deepwater Horizon oil spill that happened a number of years ago? And let me get that up on the screen. And back in 2010, it's a while ago, I was consulting. I was already teaching here at ECC. There's this massive oil spill in the Gulf of Mexico, and the name of the oil platform was Deepwater Horizon. And the government was putting out numbers, how much oil. I did my own calculation because as an organic chemist, got my interest that they were way under describing how much oil was being released. It was a lot more than what they claimed, but even what they claimed, over 200 million gallons, that's almost 800 million pounds of oil was released. That's a lot, a lot. And in order to help disperse it, they used an oil dispersant, something that broke the large amount of oil into smaller pieces and little droplets. And at that point, I wondered, well, what are they using? And it was on there. And now I'm going to teach you something. I might have mentioned, but I don't have them because we're not in the lab. There's something called the Material Safety Data Sheet, also known as MSDS, Material Safety Data Sheet. And sometimes you'll hear people call it other names, but MSDS is generally what's called. And any chemical that's produced, and this is not going to be on a test, but I like to give you some real world experience. Any chemical that's used or produced in the United States has to have an MSDS that's publicly available. And they are. And with the internet, they're easy to get to. Any chemical that's shipped, like in a tank wagon, they've got to have an MSDS with it, or if you get a box of it, and you'll get an MSDS. Now, the product that was being used was Corex, made by a company then called Nalco, which is in Naperville, and it's now owned by a French company. I think it's called the Nalco division. And I looked it up, and I saw the key ingredient in that chemical was the butoxyethanol. And I looked that up, and let's do that. And then when you're looking up, hold on one second. When you're looking up an MSDS sheet, like here, I should have put the name, then afterwards, sometimes SDS, or I like the old way, MSDS, and you'll see number of hits come through. And, oh, let's go to Fisher. This is probably a newer, and this is an MSDS sheet. And it'll always have the name of the chemical and synonyms and what category. Now, the older ones had more description, but if you notice, acute tech 4 is the worst, 1 is the least hazardous. It's got 4 on things you don't want to deal with this stuff. Well, they put in, I don't know how many million pounds of the Corex, I think it was 9517 or some number like that, which had about 60% of this 2-butoxyethanol, which here's another name for it, but I like the Iupac, 2-butoxyethanol. And this may not have it, but the older ones, if you go down, you can see firefighting, accidental release, handling, storage, and usually it shows you OSHA permissible exposure limit. When you see things this low, 25 ppm per 8 hours, that's what this means. It's hazardous. And this one, the newer ones, they don't have it, but they'll talk about effects on usually wildlife and things like that. Notice the LD50, what it will take to kill half of a population is very small amount per milligrams on the skin. Inhalation, when you see ppm after 4 hours, rats that inhaled this amount, 450 parts per million, 50% of them were dead. That's what the LC50 or LD50 is. And animal carcinogen, human carcinogen, and I saw all this in the older ones, it also attacks wildlife. Well, my parents raised me to be socially responsible, and I'm an industrial organic chemist. And so what did I do with this information? I called the Coast Guard. I got pretty high up in the food chain. Oh, it's safe. We've been told. No, it's not. Look at the MSDS. And I got talked to their chemist in charge of that, who was an analytical chemist and academic, not industrial experience. And though he was an analytical chemist and a good one, he just, oh, it's not that. Come on, look at the MSDS. Well, he blew me off. Bad mistake. So what did I do? I contacted the New York Times, MSNBC, CBS, ABC, and with my credentials, and I'm sure I wasn't the only one, and they did stories on them, and luckily within a couple days, they stopped using that. More than a couple days, too many days. Well, years later, I saw an article a couple years ago about after effects that happened to people who were on the boats cleaning that up out in the sea, and also people, they had volunteers who saved wildlife, also cleaning up the oil from the beaches. They were all exposed to that Corex, which had the 2-butoxymethanol. And years later, unfortunately, the effects in the MSDS, they were now experiencing health problems. And I contacted the author of that article, and actually was a co-author. I could find one of them. He said, let me get someone to call you, the other author, because he actually was on a boat cleaning up the oil spill, and he's talked to people. He was the one who interviewed most of the people in that article. And I talked to him, it shouldn't have happened. What was in the MSDS was that. And that's not the first time I've got the news involved when I could see from my background. I thought I'd let you know. All right. I think we've done enough chemistry in terms of lecture stuff. It's time for the lab. And today's an interesting lab. Pay attention, take good notes. If you don't, I'll put it on the video soon. Next day or two will be posted. But anyways, let's do today's lab. And I assume all of you can see Aromatic Electrophilic Substitution Lab. Unfortunately, we're not doing it in the lab itself. And this is an exciting lab because you'd be working with very dangerous chemicals. I warn you about sulfuric acid, concentrated nitric acid. You never want this on your skin because it will cause serious damage to your skin. And only once at the other school, when a student didn't follow what I told everybody, you do it this way, he got some on his skin and he had a serious burn. Even though I was able to get water on it almost immediately, but you're not going to be handling it today. But I would tell you, don't touch your face or your arms, even though you're all going to be wearing gloves that I provide. All right, when you have a benzene ring and you have an electrophile, like we did with alkyl halide and aluminum trichloride, or nitration or bromination or others, you replace one of the hydrogens on the ring with the electrophile. Now, what happens when there's a Z group on it? And somewhere aromatic organic chemists decided a group that's already on the ring, when you're going to react it, we'll call Z. And they do. And that's what I learned. That's what everybody uses. Now let's go to my whiteboard. This is in the, now, let me give myself some more space. If we have an electrophile, we have the ortho, the meta, and the para. If it goes on this side, it would be meta. On this side, it would be ortho. So there are three possible products you could get here. If it goes here, you would get this. If it goes here, this is ortho. This would be meta. And I'll explain why I'm using this terminology, product. And I'll move the last one over here. And this would be para. And what determines is the ability of that Z group to release or withdraw electrons from the benzene ring. And I'm not going to go into what does what. Organic chemists know certain type of Zs withdraw electrons from the benzene, other release it. And because of that, there's two types of directors, Z. One type is ortho para, abbreviated OP. The other type is meta. So if you have an ortho para director, you'll get these two products. If you have a meta director, you get these. Now, there's something I need to talk about. Remember, what we do in the lab is never going to be on test in the classroom, but it's still stuff I'd like you to learn about, which is why I created these labs. Now, sometimes if Z is real big, Z can be big, it blocks the ortho position. And therefore, you don't see ortho products, even though it's an ortho para director, you only see para. So that happens. Think about if you're trying to go outside a door of a room and there are 20 football players standing in front of that door, it's hard to get through. And if there's another door that goes to the same hallway in that room, you'll take the easier one. So sometimes you can have ortho para directors, but you don't see any ortho product. Now let's talk about today's lab. And today's lab, the Z group you're going to use is bromine. And you're going to investigate what type of director bromine is by reacting it with nitric acid and sulfuric acid. And this is nitration. Now, this is going to put a nitro group on the benzene ring. Now, I'm not going to give away where it's going to go, so I'm going to draw it this way. This is just my way of saying I'm not going to tell you where it's going to be. It's going to be somewhere on that benzene ring, and you'll make bromonitrobenzene. Now, before we talk about this reaction, why nitric and sulfuric? Well, let's look at sulfuric and think of it as an acid H+. Let me write nitric acid a little differently. Hint, you should know this. Again, not for the test, but for the lab. And think of nitric acid as this, HNO3. Now, how does this react? This is an acid, and it adds to the nitric acid to make the following. And you get this cation. Now, if you look in this molecule that I've just made, you'll see something familiar. Everybody see that? What's H and O? Two H's and O. H2O. It's water. And whenever you can form a stable leaving group in a molecule, it says, I'm out of here. So you lose water. And what are you left with? The nitronium ion. And this is what attacks the benzene ring and why you put a nitro group on there. So why do you react sulfuric and nitric acid first together? Because you form the nitronium ion. Now, in this lab, all the isomers of bromonitrobenzene are solid, and you can isolate them and take the melting point and determine which isomers you have. Now, this semester, I don't have a chance to show you how to purify a solid. That's called recrystallization. So any product you get is going to be a little impure, which means the melting point will be a little lower than the literature value. In the lab, I talk about meta-director, ortho, and para. And I notice here, you'll react with sulfuric and nitric, nitrate the benzene ring, and determine if the ring is an ortho-para-director. Again, there are only two types. Even if you only get para, it's still called an ortho-para-director. Or if you only get ortho, that's rare because that doesn't happen. Usually if Z is big enough, it will block the ortho position. So if you only get para, it's still called an ortho-para-director. But if you get meta, it will be meta-director. And if you notice here, I didn't give it away. What are you going to get? Let's go through the procedure you would have done. By the way, I highly recommend you watch these YouTube videos to see what you're missing. Now, if we were in the lab in a round bottom, heat up some water in a beaker and boiling chips. Why do you put boiling chips in a beaker? This is a hot plate. Oh, but I tell you, Dr. White will never be an artist. You can always laugh at my drawings. And here's water. And you put boiling chips in there because in glass, it's very smooth. When you boil something in glass, in metal, no matter how smooth it feels to your touch, it's really rough at a microscopic level. And that forms spaces areas where bubbles can form. What's boiling? When you form water vapor in the liquid, and they come up when the vapor pressure is equal to the atmospheric, that's the boiling point. Well, if you don't have boiling chips in there, because glass, even when it's scratched, is still smooth, you can get these monster bubbles coming up and splash all the liquid. So, and I'll teach you more about that when we do a distillation. So you start water boiling, and then in a round bottom flask, you add 3 milliliters of concentrated sulfuric using a glass funnel, and then cool it nice for 5 minutes. Then slowly add small amounts of the concentrated nitric acid while it's still being cooled in ice. What the student who had an accident, the only time I ever had an accident, and I've done this with hundreds of students, didn't use a funnel. I can't even get liquid into a round bottom with an eyedropper without a funnel. He was nervous, couldn't get it in, got nervous, somehow twitched and squeezed the eyedropper and got it on his forearm. Anyways, I keep on going around the lab when we're doing this lab face to face, use a funnel, take your time. Well, anyways, you let that sit for a little while. And then while it's still cold, you add the 1.6 milliliters of bromobenzene, one portion, stir it for a minute, let it come to room temperature for about 10 minutes, maybe 5 minutes, then put it in boiling water. Now, first time I ran this reaction in the lab, teaching it, because I didn't do this as an undergrad, I don't remember it, all of a sudden brown smoke started coming out of the top. We're in hoods, and I found out that was nitrogen dioxide, it's an impurity, a side reaction. And I used to tell students, and if I teach it again next time I teach at ECC face to face, I'll warn you, you see a brown smoke, you're in a hood, you're safe. And then After that, you take it out and you let it cool. You'll see a solid in there. Now, because of the length of time of our labs, which is only an hour and 50 minutes, at College Page, our labs like this are 2 hours and 50 minutes. We don't have time to isolate and do the melting point. So I come around and give you the melting point if you had been in there. And I asked and I looked to see, there's my initials again. And Sal, you got the melting point if you had done it. Given to you is this. Here's what you have to do. 1, you have to identify which product you get. It's one of these 3. Next, you answer these questions. And that's today's lab. If I look at the clock, we're out of here early today. And lab days, we usually go 50 minutes, but I wanted to get caught up. We're caught up. And with that, I will remind you, please get their labs in. Labs that are due today, get them today or tomorrow to me. Upload them in D2L. Another thing, since I didn't mention it on Monday, or if I did, I forgot, but I don't think I did. Next Wednesday, make sure your web camera is fired up and working for those who haven't been using them, because what I'm going to be doing is using breakout rooms again. We'll spend some time where you get to meet your colleagues. I get to go into breakout room and talk to some of you and find out about you. If we're in the lab today, I'd be walking around making sure, A, you're doing it right, and 2, talking to students, and you get to know me and I get to know you. But we can't do that via Zoom now unless we do breakout rooms. And don't forget, tonight, I have my office hours. If you need help, let me know. By the way, if you can't make it to my office hours and you really need help, let me know and I'll try and set up a special office hour, because I've got Zoom accounts both here and at COD that we can do other times. But I'd rather you come to my office hours on Monday, Wednesday night. And with that, I'm done. Gang gesund. I'll see you on Monday. Y'all have a healthy, nice rest of the week and weekend. If you notice, no snow. I'm tired of snow already. Actually, I'm tired of Monday after I had class. I spent some more quality time with my driveway and a shovel. But anyways, no snow. It's supposed to be warm. With that, I'll let you go. Gang gesund. Goodbye. Be healthy. And I'll see you on Monday.